Hello and welcome back to Calculus 2. This is the part 2 of 8.2 integration by parts. So we derived integration by parts. We had this as a formula. Then we derived it again. Got the same formula. And then we talked about integration by parts where we set up u and dv by taking everything from here and then working out the formula to reduce it to the integral that it's easy to integrate. And then we checked. And did that one more time. So now we're going to do more examples and then switch to definite integrals and so on. So let's see another example of integration by parts. So far you guys had two examples which both featured u equals x, right? Both of these were u equals x, and then the rest went into dx. This next problem looks similar, but you can't solve it the same way. It still has function x, it still has another function. So we had x times e, x times sine, and technically now we have ln x divided by x. Well, it's x to the 10. So this is a great problem for us to actually see when stuff goes wrong, it goes wrong quickly. If you make a wrong choice, and in this case making u x to the 10, because you are used to having u to be x, and you leave the dv to be ln x dx, why is this a wrong choice? Well, there are two reasons why, and I love this problem because both reasons appear at once. First off, you can't integrate dv. dv is the part to be integrated. And if you look at the dv, you're supposed to integrate ln x. You don't know how to integrate ln x. It's not a basic integral, right? So you can't proceed because you can't get v. The other reason why, this one is a little bit tougher to see, is we see your x to the 10 is in denominator, right? When you differentiate, this was supposed to be 1 over x to the 10. There we go. Which is x to the negative 10. So x to the negative 10. When you differentiate x to the negative 10, it becomes x to the negative 11. So instead of losing a power, you're gaining it, and it's making it worse, obviously. See, the case why we were able to do this before, you had that extra x that was bothering you, but then differentiation killed that x, and now you have no x to integrate. And the same thing was with the sine. Here it is. X is bothering you. As soon as you go through the procedure, x would die in this substitution, and then you end up with the integral with no x. So these x's were getting killed by the substitution up there. But now if you have x to the negative 10, when you differentiate it becomes negative 10 x to the negative 11, and you just made it worse, right? It didn't decrease the power. I mean, the power did decrease because clearly negative 11 is smaller than negative 10. But the trick is that it is not erasing x's, and then that's the issue for us. So clearly this is a wrong choice, and you have to swap. So now you have to put ln here, and x to the negative 10 in here. And now when you integrate, du is 1 over x dx, and v, now when you integrate this, you get plus 1, so it becomes x to the negative 9 over negative 9. So now, when you put that arrow that shows the formula, you have ln x divided by negative 9x to the 9. Then you have a minus integral. This is negative 1 over 9x to the 9 times 1 over x dx. The minus is going to jump on ln up there. So now you have negative ln x divided by 9x to the 9. The minus sign jumps outside, so it's a plus integral. Oh, you can also kick 1 over 9 outside. There we go. And now it's integral of just x to the negative 10, because you have x to the 9 and another one that's x to the 10. The denominator goes up as negative 10. And now you can integrate because it's just a basic integral. So this is negative ln x divided by 9x to the 9 plus 1 over 9. And now when you integrate this, right, you get to add 1. So it's going to be x to the negative 9 divided by negative 9 plus c. Only 2 of you in the class out of 20 forgot plus c on 2 problems. So that was not bad. Negative ln x divided by 9x to the 9. And now we have minus 1 over 81 x to the 9 plus c. Now we can still do better because we have a common denominator here of 81 x to the 9. So 81 x to the 9, we need to multiply by 9. So negative 9 ln x minus 1 plus c. And if you want to be really fancy, you kick the negative in front. And you have, you can list 1 first. 1 plus 9 ln x, so there's no confusion. And then 81 x to the 9 plus c. That will be the boss level of simplifying. Now, some people would like to have it themed, so they don't put the 9 over here. They put x to the 9 because you have x to the 9 in here. But it doesn't matter. I mean, from now on, it's just cosmetics. So that's it. That's ln x divided by 10. What we did is we had to put ln here because, remember, you can differentiate anything. Integration, not so much. If you put ln in here, the issue is that you can't integrate because you don't know what the integral of ln is. Let's find out. What's the integral of ln x dx? Well, clearly it's sitting in 8.2, so it better be some kind of u sub. But what do we put? U equals and dv equals. Now it should be easy because I did explain the previous problem. What goes where?
Said u equal to ln of x.
Excellent. And what's the dv?
Yes.
Just dx. Yes. Remember, you can't put ln in dv because dv gets integrated. And we don't know what the integral of ln is, right? So we better put it in for differentiation. And now du is 1 over x dx. And over here, v is just x. Integral of 1. You put your arrow here to help with the formula. So you have x ln x, that's uv, minus the integral of x times 1 over x dx. Oh, they cancel. Look at that. Beautiful. Dead, right there. So we have x ln x minus, and now you just have integral of dx. Well, that's x. So x ln x minus x plus c, and then if you want the to factor out x, you can, x, and then you have ln x minus 1 plus c. Now this one is perfectly fine to keep right here. You don't have to do the factoring. Especially, I don't want you confusing this with x minus 1. It's completely different. They're not the same. Not the same. So be very careful with that. So maybe this is the best form, but then depends on how careful you are with mathematical notation. So whichever form. And, you know, the students tend to memorize this answer because, you know, integral of ln does show up. But again, it's a two-step solution to get it if you don't know it. So it's okay. Great. The next creature that we are going to take a look at is x squared cosine x dx. So we had x times sine, and we were able to solve it in 2 lines. Now this one is x squared. So what should we do now? Anyone? Yes. So u equals x squared and dv equals cosine x dx. Now, why is that so? Well, first off, think about this. If you put x cubed for dv, x squared for dv, what's going to happen to it? It's going to get integrated. So it's going to become x cubed. Bigger headache, right? You don't like that x squared. If x squared wasn't there, problem is a joke, right? Integral of cosine is sine, you are done. This x squared, right? Well, try and kill it. Because derivatives, right? Derivatives kill exponents on polynomials and eventually kill a polynomial. Take enough derivatives, every polynomial goes away, right? So du becomes 2x dx and v becomes just a basic sine x, right? And we put our trusty formula. So now you have x squared sine x minus the integral of 2x sine x dx. We didn't really got rid of the x, right? So what now? Again, that's it, right? You hit something with a hammer, it's not done, hit it again, right? So now, orange, u equals 2x, dv equals sine x dx, du equals 2dx, v equals negative cosine x. And now, look at that too, that du, right? It doesn't have power. It doesn't have x at all, actually. So now with the formula, don't forget to copy the rest of the problem, right? So you have to copy x squared sine x minus, and now in parentheses, you have your negative 2x cosine x minus the integral of 2 times negative cosine x dx. So it's a lot of negative signs and a lot of things that you have to take in consideration. So what do we have? x squared sine x. Minus and minus gives me plus 2x cosine x. And now you have 3 minus signs. 1, 2, 3 minus signs. Give me a minus, kick 2 outside, cosine x dx. And I can finally solve the problem. Because integral cosine is just sine, so it becomes x squared sine x plus 2x cosine x minus 2 sine x plus c. And that would be the answer. What do you do with this? You differentiate and make sure that it ends up being this whole bunch of stuff is going to cancel. You guys have a product rule, you have another product rule, vanilla derivative over here, that's 0. So 2 product rules and a basic derivative. When you are done with all of that, it needs to collapse into x squared times cosine x. So now for these that have higher exponents, well, exponent is 2, and we did 1, 2. The amount of integration by parts that you are going to chain in one problem is equal to the exponent of x. So you definitely don't want to see x to the 5 over there, right? Because that's going to be a problem for, carpal tunnel and stuff like that. Even though we're going to have some carpal tunnel problems today, but we don't have yet. Good. Let's take a look at some of these cute limit problems that they have in here. They ask you to integrate. Let's do at least 2 of these. You can try. Well, let's do the vanilla one first and then. So how about 0 to pi of x sine x dx? So try this one on your own. You know you have to set up u and dv and all that good stuff. So you should be able to do this right now. So you should have the same answer as before, just now you get to calculate limits. So y equals x, dv is sine x dx, du is dx, and v is negative cosine x. Put our arrow for yes, and now we have negative x cosine x minus, and minus from there will be a plus, integral of cosine x dx. Everything will be computed from 0 to pi. We still have one more integral to solve, so negative x cosine x plus sine x, and now it's not plus c, it's 0 to pi. Now sine x will die with 0 or pi, so we don't care. 0 will kill this x over here and make it into a 0, which kills the whole term. So the only thing I need to compute is this term with pi. So this one, 0 and pi kill it either way. This one is just killed by 0. So the only thing I have to calculate is pi. So I have negative pi cosine pi. Cosine pi is negative 1 for the total of pi at the end. One more definite integral, and then we are going to move to the last problem for this section. This one now is integral 1 to e squared of x squared ln x dx. Be right back. It's okay to talk and help each other. What can you tell me about this problem just by looking at it? Gotcha. What do you mean? Why? Once. This is the evil one with ln. You don't get to integrate ln. So your u is not going to be x squared. Your u is ln. X squared goes in the dv part. Gotcha. Gotta be careful. This is the one. The ones with ln's are the ones that are flipped. So that's true. Okay. So u is ln x, dv is x squared. So this one is flipped because it has ln in it. All right, put the formula together and try to compute. No pressure, you have 18 seconds, go. Okay, let's see. So we have 1/3 x cubed ln x minus 1/3 integral x squared dx. Because x cubed divided by x is x squared, 1/3 goes in front, is good. We still have 1 to e squared as our limits. So now this becomes 1/3 x cubed ln x minus 1/9 x cubed from 1 to e squared. We have, plug in e squared, so that's 1/3 e to the 6 ln e squared minus 1/9 e to the 6, no plus c, right? We have limits. Ln e is just 1, so you got a 2 out of there. So this is 2/3 e to the 6 minus 1/9 e to the 6. You can factor out e to the 6, and in parentheses you have 2/3 minus 1/9 times 3. So that works out to be 6 minus 1 is 5. So 5 e to the 6/9. A little bit of mathematical gymnastics there to get to these calculations, nothing too bad. So be careful with the ln. Pretty much all others will have x to be in a u position. It's not a rule. It's not a rule. Most of the problems work out that way. When you have ln, ln goes there. Let's take a look at a very interesting problem. In most of these problems, you put u equals x. Not all, but most of them. And when you don't, stuff works out nicely over here. They cancel and they combine and so on. Right? But in general, you always have the same thing happen, and that is the leftover integral over here is easy to deal with once you, right? Over here, x and sine x, so x goes away. You're just left with the trig, easy to deal with. If you do the e's, the same thing. Look at this problem. Which one of the two can you place for u and then take the derivative and it goes away? Which one? Neither. Derivative of e to dx is e to dx forever. The derivative of cosine flip-flops between sine and cosine. No matter which one you pick, it's going to be bad. Excellent, let's do it. My type of a problem, right? And stuff goes wrong 100% of the time. So let's go. U is equal to e to dx, and dv is equal to cosine x dx. So du is e to dx dx, and v is sine x. We put the arrow like that, and we get e to the x sine x minus the integral of e to the x sine x dx. And you look at the fruits of your labor, and you realize achieved nothing, right? You had exponential function and a trig function. You went through the horror of this procedure, and you ended up with the same thing. Well, now it's sine. So what now? Exactly. You just do it again. What's the definition of insanity? Doing the same thing over and over again, hoping for a different outcome. Well, it's Calc2. We're all insane. Let's do it. U equals e to the x. dv equals sine x dx. du equals e to the x dx. And v is negative cosine x. And we put our arrow. Copy e to the x sine x minus, and now in parentheses over here, I have negative cosine, well, negative e to the x cosine x. Minus and minus gives me a plus integral of e to the x cosine x dx. And when I simplify this, it becomes e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. And good. We made it. Please tell me you know the next step. Do you?
You notice it's cyclical and you do something different? Or do you do it again?
So what did you say you noticed?
You notice it cycles.
It cycles. Okay, can anyone use that fact and do something absolutely crazy right now that you have never done before with integrals to solve this? Yes! Nice! This problem started here. And it has all of these equal sign, making this equal to all of that, and we can just ignore everything in between. What you can do now, and you, as I said, completely insane, and as a student, I just sat there staring and saying, someone figured this out, actually. That was the first thought that crossed my mind. You take this term, and you add it to the left-hand side. So there will be no equal sign over here anymore. We are breaking that. We are breaking the cycle of equal signs. I'm going to add this, or no, not add, let's say move. Move this to the left side. So now you will have two of them. E to the x cosine x dx. Nice one. Go on. And then you have e to the x sine x plus e to the x cosine x. Well, now, a triplet. So now, what's the difference between this and this? What's the difference? There's a 2 in front, right? So you just need to get rid of that 2. And you divide. So, the integral of e to the x cosine x dx is equal to, you can factor out e to the x. E to the x over 2 sine x plus cosine x plus c. And there's your answer. You have never done integration like this before. It's a completely new way of thinking with integrals. We took the part of the solution integral on this side and moved it to the left side to add it to the original integral because they were the same. And you ended up with 2 of them. And then you just divide the 2 you don't want, which is right here now, and there you go. Problem solved. Box. So study this problem. Obviously, the other iteration is to have e to the x sine x, which will pretty much give you the same answer with different signs. And then you can also take a look at the book, because in the book they're asking you what is the e to the 3x times cosine 2x, just to make it more annoying. So you have to chase those constants, right? When you integrate e to the x, you will get e to the 3x, you get e to the 3x over 3. When you differentiate e to the 3x, you get 3 e to the 3x. So another challenge would be to actually put sines and cosines as u, and put e to be in a dv spot, and see if that's going to solve the problem, and so on. This is a lot of tricky work, 2 integration by parts, and so on. If you were allowed to use complex variables, this is one line in complex variables. One line. You put equal sign twice. And you already know it. You already know to solve this in complex variables, because when I taught the hyperbolic functions, I did give you the definition for cosine in terms of e's and i's, right? I did tell you, okay, so side note, I did tell you that the cosine x is e to the ix plus e to the negative ix over 2. Sine had the 2i. So if you have this, your integral now is just e to the x times e to the ix plus e to the negative ix over 2 dx. You kick 1/2 outside, and you have your integral. When you distribute this x, e to the x, right? It becomes e, and this is now x, and you factor out complex number, becomes 1 plus I. Now, guys, I know it's a complex number, 1 plus I, but it doesn't matter. Complex number or a regular number that you are used to, it's the same rules. So you have this plus e to the x times 1 minus I, all of that dx. And you are now integrating e's. It's one-liner. Complex variables are extremely powerful, right? Extremely powerful. But again, you have to learn enough of the real math, and then you can move into the complex domain. Now, complex domain is used, your alternating currents, like Tesla figured out how to shovel these complex variables and create alternating currents using those, right? So our technology is based on the mathematics of complex numbers. So it's important. So now this integral is a joke, right? Because it's just 1/2, and you know when you integrate this, you get e to the x 1 plus I, and this is a constant, so 1 plus I in the bottom. The same way, like if you integrate e to the 2x, you get e to the 2x over 2. Well, now your 2 is not a 2, it's 1 plus I. It's the same rule. It doesn't matter. So you just get that, and then plus e to the x 1 minus I divided by 1 minus I plus c. Boom. So it's a two-liner, right? Very easy. One line, actually, because this is your original problem, and then these two you can fit in one line, and you have the integral. It's extremely easy to deal with these things, right, when you go to the complex domain. Again, we don't deal with complex, so you don't have to know anything in blue. Just wanted to show you how easy this whole process and the problem is. And we didn't even use any special integration. You integrated e to the ax, right? A being a real number or a complex number, it doesn't matter. So these are the things that you guys have, that you guys can consider. And that concludes the integration by parts. So integration by parts, it's this formula. Let's go all the way up. I'm just going to keep it for the end of the class. Give you one. That's the integration by parts formula, where we said that u and v are actually functions of x. And experience, your experience will determine, right, how fast, how well you're going to do this, obviously. So the more you practice, the better off you will be. Now, I'm going to warn you one more time that your lab 2 is extremely, extremely long. It will have a whole bunch of these 30 problems, maybe, for integration by parts alone. And it will ask, I mean, when you calculate A, B, C, D, E, whatever it has in each problem. They have you make wrong choices. They have you make good choices. They make you compare and say why the wrong choice is a wrong choice and right choice is a right choice, which is when you learn that, you know, the polynomial loses the power and goes away with the derivative, but then when you put the ln, it should swap the places and so on. So it goes through the variations of these to really, really learn this stuff. So lab 2 is very good to practice this. Now, there's also other stuff in lab 2, but primarily it's this. All right, break time, and after we come back, trigonometric integrals. Yes, trig, woohoo.